In this video, we're going to talk about definite integrals and the fundamental theorem of calculus. So two big objectives. Under definite integrals, we're going to answer conceptual questions about definite integrals. We're going to sketch the graph of an integrand and approximate the area using Riemann sums. I did a little bit of that last time. We're going to sketch the graph of an integrand and use geometry to evaluate the definite integral. I did a little bit of that last time as well. We're going to evaluate definite integrals using the property of definite integrals. The fundamental theorem of calculus, I talked about that a little bit last time. We're going to answer conceptual questions involving the fundamental theorem of calculus. We're going to evaluate definite integrals using the fundamental theorem of calculus. We'll find and verify area functions. We'll find areas bounded by functions, the area between two curves. So let's go ahead and look at this motivating example. Once again, we're going to use the example like we did last time of the function y equals x from 0 to 6 to talk about the fact that we could use the geometry formula a equals 1/2 of base times height to get the answer of 18 units squared like we did last time. But now we're going to state the area here as being equal to the definite integral from 0 to 6 on x of between x and 0. So x minus 0 is x dx, like that. And that'll be the new way that we write it. And we'll also get the same answer of 18. I'll show you how we'll do that later. But this is going to be the idea of, we know that we can use this geometry technique for a right triangle if it were a line like this, but we're going to see that that doesn't work so well for curves. So B here, let's consider now f of x equals x from x equals -3 to x equals 6. We're going to actually have to see two triangles here. So -3 and +6. And so here's triangle 1 over here and triangle 2. And let's see if I can shade this here in yellow. And let's shade this here in pink. Like this. So that you can see the two triangles that I'm working with. And let me get back to my pen now. So for triangle 1, we have A1 is going to be equal to this base is going to be 3, and this height is 3. Now they were in the negative direction for both of them, but we need to take their absolute value so we get their distances. So this is going to be 3 times 3 is 9 over 2 square units for the area, because area is always a positive value. T2, we're going to have area 2 is going to be 1/2 of 6 times 6. We already know that is going to be 18 square units. We did that one up here. And so if I wanted the total area, that would have to be 9/2 square units plus 18 square units. 36 plus 9 is 45/2 square units. Looking ahead, we're going to have to define this one with a definite integral here as the opposite of -3 to 0 x dx, because this area is below the x-axis. We need to multiply it by -1 to make it a positive number. And then we'll need to add that to go from 0 to 6 of x dx. And that'll add together to give us 45 halves looking ahead. So the key thing that we're going to talk about here, one of them coming up, is why we need that negative sign when the function dips below the x-axis. So the net area, definition here, consider the region R bounded by the graph of a continuous function f and the x-axis. The area beneath the curve between x equals a and x equals b. The net area of the region R is the sum of the areas of the parts of R that lie above the x-axis minus the sum of the areas of the parts of R that are below the x-axis. So there it is right there. So the sum of the parts of the areas that are above the x-axis, that would be T2, minus the area that is the part below the x-axis, that would be T1. That will give us our net area here. So for part B, above, the total net area is equal to A2 minus A1 is going to be equal to 0 to 6 x dx minus -3 to 0 x dx. And we'll solve those integrals in a little bit here. But as another example here, if we had a curve that looked like this with A, B, C, and D, and that makes an R1 and R2 and an R3 like this. This is going to be f of x, and it can keep going on both ends here, but I'm only interested in this part between A and D. Then for this, we're going to have the region from A to B, f of x dx, plus the region from C to D, f of x dx, minus the region from B to C, f of x dx, because region 2 here goes below the x-axis. This is region 1, and this is region 3. All right. Now let's look at our definition of our definite integral. A function f defined on the closed interval a to b is integrable on a to b if the limit as n goes to infinity of k equals 1 to n of f of x sub k star times delta x sub k exists and is unique over all partitions of a to b and all choices of x sub k star on a partition. Follow the pattern of how we set up the problems last time, and we'll do that again this time, I think. So I did one of those at the end of the notes last time with the limit definition of the antiderivative using infinitely many rectangles of infinitesimal width. The limit is called the definite integral of f from x equals a to x equals b, which we write as this Riemann sum here with the limit in front of it is equal to the definite integral from a to b, f of x dx. And the important thing here is that n is going to infinity here. So this definite integral will equal the exact area under the curve. No approximations like the last video where we did lower sums and upper sums and midpoint sums and said that we were getting good estimates but not exact answers. So let's look at a function that curves some like this, and we want to go from A to maybe B over here. Like this. And we could try and do this with rectangles, with left midpoints and right midpoints and so on. But we're just going to keep cutting those rectangles down so that they have infinitesimal width. And when I stack them next to each other, they go up and just touch the function. And they're basically one-dimensional now since I've squeezed out all the width. And it's just like I'm shading in under the rectangle. So I'm going to get blue here. Instead of drawing all these rectangles, it's like I'm going to just color in the area of this curve with all those rectangles. Pretend that I've made rectangles that are all stacked next to each other and are this blue highlighter here instead of the dark blue pen. And you're going to get the exact area that way. I'll eventually shade this and it'll become the entire area will be there. So the fundamental theorem of calculus tells us that if f is continuous on the closed interval a to b and f is any capital F is, so this is a lowercase f, I should be saying, if lowercase f is continuous on a to b and capital F is any antiderivative of lowercase f on a to b, then the definite integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a. We're going to choose the antiderivative with no constant. Choose the antiderivative with no constant of integration. Because the constant of integration is going to be the same. You're using the same capital F here and here, so the constant of integration is going to go away. So f of x is the derivative of capital F of x. Or another way to say that, f prime of x needs to be equal to lowercase f of x. So recall from our motivating example that we want to find the area that was from -3 to 6. We're going to find the antiderivative of, or the integral from -3 to 6 of x. And you're going to see that it's not the same thing as that area. We want to show you that. So if I were to use the power rule for antiderivatives, and I think we talked about this last time, gave a sheet with some stuff here. So this right now has a power of 1. We're going to increase the power by 1 and divide by that new power. Then we're going to plug in our limits of integration. This is going to be 36 over 2 minus 9 over 2 is going to give me 27 over 2. And that doesn't match our 45 over 2 that we wanted as our answer. Look up here. Why is our answer different? Our answer is different because if we just do the one whole thing from -3 to 6, we're taking this negative part as being negative. We have these things in math called vectors where the sign is important and they cancel out negative things that are vectors, zero out positive things that are vectors. And so this is something where the positives and negatives are meaningful and opposite signs are going to undo one another, and we're going to see what's left over. And we only got left with 27 over 2 when we did this. Well, how do we fix that? We already talked about that. If we wanted to get the total area, we would have to use the net area formula, and we would have to say, okay, I want the part from 0 to 6 minus the part from -3 to 0, and I'm going to get x squared over 2 from 0 to 6 minus x squared over 2 from -3 to 0. I'm going to get 36 over 2 minus 0 minus 0 minus 9 over 2. It's going to give me 18. Well, let's just call that 36 over 2 for a second. 36 over 2 minus a negative is going to be plus 9 over 2. That's going to be 45 over 2 units squared, and that's my right answer. So let's go ahead and let's evaluate the following definite integrals. Number 1, 1 to 3, x squared minus 4x plus 1 dx. So we'll be using the power rule each and every time here. X cubed over 3 minus 4x squared over 2. That makes it 2 there. Plus x from 1 to 3 is going to give me 1/3 of 27 minus 1 minus 2 times 9 minus 1 plus 3 minus 1. I'm just putting in those upper limit and lower limit for each one of the x's there with the constant multiplier out front. So this is 26 over 3, 8 times 2, that's minus 16 over 1, plus, this is 3 minus 1 is 2 over 1. So I'm going to multiply by 3 over 3, and 3 over 3 here is 26 minus 48 plus 6 over 3 is 32 minus 48 over 3 is a negative 16 over 3 for that example. All right. Moving on to our next example. Actually, let's just do a little reminder here before we go on. We use this space over here that 1 over x dx is equal to ln of the absolute value of x. The integral of sine x dx is going to be a negative cosine of x. These are plus c's. For the antiderivatives here, the reason for this is that the derivative of ln is 1 over x. The derivative of negative cosine is sine. So now let's go ahead and find the area that is beneath sine from 0 to 2 pi. We're specifically told to find area here. So we're going to use the net area theorem. Let's look at the sine graph. And from 0 to 2 pi, we see that we cross the x-axis at pi. So I'm going to have to set up an integral from 0 to pi of sine x dx. And then I'm going to need to subtract from pi to 2 pi sine x dx. I don't want to just go 0 to 2 pi of sine x dx. That'll give me the wrong answer, because I'll get this positive and this negative will zero each other out. And I want the total area that I see there. So the derivative of sine, or the antiderivative of sine, is negative cosine from 0 to pi minus, and then this is also going to be a negative cosine from pi to 2 pi. So cosine of pi is -1. So -1 minus a negative is a positive. Cosine of 0 is 1. And then minus a negative, that'll be a positive. Cosine of 2 pi is 1 minus cosine of pi is -1. This is 1 plus 1 plus 1 plus 1 is 4. That'll be in square units. Number 3 asks me to find the definite integral from 1 to 2 of 2x dx. We'll pull the 2 out front. That gives me x squared over 2. From 1 to 2, that 2 and that 2 can cancel each other out. And I get 2 squared minus 1 squared is 4 minus 1 is 3. Fourth example here is to go from 1 to 3, 2 over x squared minus 4 over x dx. It's going to be 2 integral from 1 to 3 of x to the -2nd dx minus 4 integral of 1 to 3 of 1 over x dx. So that's going to be -2 x to the -1st. I'll write that over x like this. 1 to 3 minus 4 ln of the absolute value of x from 1 to 3. -2 times 1/3 minus 1 minus 4 times ln of 3 minus ln of 1 is going to be -2 times -2/3 minus 4 ln of 3 minus 0. It's going to be 4/3 minus 4 ln of 3. All right. So let's go ahead and do just another example here. If I had f of x is equal to 400 minus x squared, and I knew that this is 20 and 20 multiplied to give me 400, right? 20 times 20 is 400. So this is f of x is equal to 20 plus x times 20 minus x. I could sketch this curve, and this goes from negative 20 to 20, and it's going to have a y max of 400 up there. It's going to be a parabola like this that I'm going to be interested in. And if I want to look at the area here from 0 to 40, I know this area, then there's going to be this area that's going to be here. Okay, so if I want 4 subintervals, write the x values that define the subintervals and label them on the graph, then I would need to go from 0 to 10, and then from 10 to 20, and then from 20 to 30, and then from 30 to 40. So I could have 0 to 10. I'll get to this area between curves in a second. I could have 4 subintervals like that. Sketch the representative regions. Well, I'm going to have, let me just shade them in 2 colors here. I'm going to have a R1 and an R2. And let's shade this one in yellow. Let's shade this one here in pink. And that pink one I'm going to have to subtract with the net area formula. So we're going to say A1 is equal to 0 to 20 of f of x dx. A2 is going to be negative 20 to 40, 400 minus x squared dx. Then I can add those together to get my net area. Actually, I should do all 4 regions here. So this should be 0 to 10, and then A2 is 10 to 20. A3, we're going to have a negative 20 to 30. 400 minus x squared dx, and A4 is a negative 30 to 40. 400 minus x squared dx, something like that. And you can calculate each of those. Then you can, if we used Riemann sums with left endpoints, right endpoints, or midpoints, we could state the approximate net area. If we used definite integrals, how I had set this up here, we can find the exact net area. So we would use Riemann sums with left endpoints, right endpoints, and or midpoints to give approximate net area. We'd use definite integrals for the exact net area. All right, that's just bringing a bunch of ideas together. Let's go ahead and move on to area between curves. So just if I set this up and I have f of x, and I have g of x, and I want this area that's between them right here on this interval, say that this is A and this is B, like this, and I'm only interested in this region, then I'm going to take the definite integral from A to B, and since f of x is above g of x here, I want f of x minus g of x dx. If I had a place in here, let's say, where I wanted, say, C here, right? Where g of x is above f of x, then B to C, I would have to get area is a positive number, so I always need upper minus lower, like that. And so I'm using the net area idea that anytime that I am finding an area, I need upper function minus lower function. We didn't do anything here for, right there's the formula right there. So what if the curves intersect? And I showed that. You find the points of intersection by find the points of intersection by setting f of x equal to g of x and solving for x. They may intersect more than one time. So like I was saying, if I was going from maybe from this might cross like this again up here at C, like this. So I may have this bounded region here, and then I may have this bounded region here that I'm interested in. So I'm going to have to maybe go from A to B of f of x minus g of x. And then I'm going to have to go maybe from B to C of g of x minus f of x. And find the point of intersection, set f of x equal to g of x, and solve for x. Let's look at an example here. Find the area of the region bounded by the graphs of f of x equals 5 minus x squared and g of x equals x squared minus 3. So I don't need a graph, but I'm going to put a graph up here for you. 1, 2, 3, 4, 5 minus x squared is going to come like this. And then x squared minus 3 is going to come like this. It's going to intersect over here. It's going to intersect over here. These should be at the same place, and they're not. There we go, like that. And I'm interested in the area, the bounded area between these two curves, which is going to be there to there. So 5 minus x squared equals x squared minus 3. Let's bring everything over to the side to make x squareds be positive. X plus 2 equals 0, or x minus 2 equals 0, x equals negative 2, or x equals 2. So I know this is at negative 2, and this is at positive 2 for the boundaries of my region. So I have negative 2 to 2 with f of x minus g of x dx, like that, upper minus lower. So this is going to be -2 to 2. 5 minus a -3 is 8. Negative x squared minus x squared, that's minus 2x squared dx. So this is going to become 8x minus 2/3 x cubed, evaluated from -2 to 2. Let's stick 2 in there, and I get 16 minus, actually, let's do it this way. 8 times 2 minus a -2, and -2/3. 2 cubed is 8, minus a -2 cubed is also 8. So this is 4 times 8 is 32 over 1. 16 times -2 is -32 over 3. So this is 3 of those, minus 1 of those is 2 of those. 64 over 3. And that's going to be units of area, so that's units squared. All right, that's it. And that took us all the way up through the beginning of chapter 7. The only thing that I'm going to come back and talk about next time that we haven't talked about yet is how the chain rule plays a role in integration with what we call U substitution. We've only done basic integration here where we have x to the n, but what if we have a function of x raised to the n? We've talked about 1 over x. What if we have 1 over a function of x? We've talked about sine of x. What if we have sine of a function of x? Those types of things. What if I replace my basic variable x with an f of x, like in the chain rule, with a composition of functions? And how does that affect how I integrate? That'll be our topic for next time. See you for the next video.